Hi, welcome back. In this lecture, what we want to talk about is how to make your PIC do what I'm doing now, to light up LEDs. On your PIC, that's this guy right here, there are a whole number of pins. And many of these pins have a functionality called digital input-output. If you want to light up an LED, then you're using the digital output setting. And what the digital output setting simply says is if I'm using this pin as an output, do I want it to set it high, the 5 volts of the board, or low, the 0 volts on the board? When this is set high, current can pass through an LED and a resistor to ground, and this LED will light up. So I have this pin active and set to high, 5 volts. On this side, I'm using 2 pins, pardon me, and a bicolor LED. A bicolor simply is 2 LEDs, a red and a green LED, in opposite directions. I'm using 2 pins. And with the 2 pins, what I get to do is I can make one pin high and one low. The electricity or current goes through in one way, gives me one color. When I flip the polarity of the 2 pins, I can make current go the other way, and I get the opposite color. So here, it's blinking between red and green. It looks kind of whitish to you because of how bright this is. And one of the things to note, when you have an LED like this, if you make it blink on and off very quickly, faster than essentially you can react, you're going to see a blend of color. Red-green will be orangey, pinky, yellowish, depending on the sort of blink rate that you have. We're going to talk about the wiring and the programming in detail next. So let's talk about how I actually made those LEDs light up. So we're talking about a feature of our PIC called digital output. And what we typically do is, the easiest thing to do is make an LED flash on and off. We do have to talk about the chips a bit to understand that. First of all, here is the pin diagram for our PIC. Now, you'll notice that each of the pins here has a name. Those names refer to what features the chip can use. The digital input and output pins and feature all start with R. For instance, RA0, RA1, RA2, RA3, RA4, RA5, RA7, then RA6. Those guys, altogether 8 pins, 0 to 7, are called port A, and they're all for digital input-output. They have other features as well. You write the program to say, I want this pin to have this feature. We'll show you how to do that in a moment. There are also these pins called the C port, or port C. I was using this guy and these 2 guys to light up the one-way and bicolor LEDs. And there's also a port B. Okay, so knowing the different pins and that they have different names will be very helpful to us. Let's talk a little bit about electrical circuits. When you have a resistor in a circuit, current will flow, or more precisely, conventional current flows when the voltage is high on one side and low on the other. This is the symbol for ground, 0 volts. This end could be the, the long line of +5 pins, or it could be one of our digital output pins set high. For this very simple circuit here, it obeys Ohm's law. The voltage drop of 5 volts across it the current will be determined by the resistance of this resistor used. This is called Ohm's law. One thing to note about our computer chip, it's not like a battery. It's more of a control, and batteries can supply lots of current, but not our computer chips. The maximum current from a digital output pin is about 20 milliamps. If you try to draw more than 20 milliamps from one of the pins or from a bunch of the pins at the same time, you're going to have problems. So that means if this was 5 volts, then the maximum resistance you could have here would be about 250 ohms. That means if we do circuits and we want to protect our pin by not drawing too much current, we need about 200 ohms or 250 ohms resistance there. Generally, when we attach any elements, we're going to always need to have a resistor in there to make sure we're around 250 ohms. Let's talk a little about LEDs. Here are some pictures of LEDs. They can look all different sorts and sizes. One thing about LEDs is that they're one-way devices. They only let the conventional current travel one way. If you try and have the current go in the opposite way, nothing happens. Here's the schematic diagram for an LED. Notice it's like an arrowhead and a flat side. Conventional current can go this way, but not the opposite way. These are the symbols for the emitted light. So this is the symbol for an LED. So when this end is high, this LED is oriented the correct way, and this is low, then current flows and this emits light. If I made this end high at 5 volts and this end low at 0 volts, the current could not flow. This effectively becomes an infinite resistance. Now, when you have a working LED, it only works if the voltage across it is at least 2 volts. Okay? If I had 1 volt here and 0 volts here, that LED wouldn't work. Would be no light coming from it. You need at least 2 volts here. So that means the voltage over this resistor, if this has to be about 2 volts, then this will be about 3 volts. So the resistor that you would need in that case would be 3 volts over the 20 milliamps, would be about 150 ohms. You'd need a buffer resistor, we would say, of about 150. 200's fine, 300's fine, anything like that. We're going in our circuit, this would be connected to a pin. We turn this pin on, and then it comes off. If I set this low, 0, 0, no current flows, and the LED is off. As I mentioned at the start, a 2-color LED is actually 2 LEDs connected in parallel, but with different orientation. When this pin is high and this pin is low, the conventional current goes this way, so this green LED would light up. On the other hand, if this end was high and this end was low, the conventional current goes in the opposite direction and this one lights up. Now let's look at the code that you would need to make one LED be on, the one-way LED, the red LED I used earlier, and make a bicolor switch on red, green, and back again. First of all, we include the XC library and always our configuration bits. Here in the main, these are the important quantities that we need. Okay? So this bit of code right here says the pin RC3, we're going to make it an output. Notice this says tris C. Okay, so the C matches the C here. This makes it an output pin. So it's telling the PIC the function of that pin. And this one, port C bits.rc3 equal to 1, it makes it high, 5 volts. As long as we've correctly put an LED into that circuit and connected it to ground, then that LED will light up. Here we're using the RC4 and RC5 pins. So they're both configured as outputs. Inside the while loop, I turn the pin RC4 low and RC5 high. So depending on the orientation of your two color, let's say that's red comes on. I have a delay, and I'm going to talk about delays in a moment. What this just says is wait. And then I switch the polarity of the pins. So now the current goes the other way, and the green light comes on. A delay, keep that so. And then we go back through the while loop. So this goes on forever. So the LED flashes on, flashes off, flashes on, flashes off. If I wanted to use pin RA0, let's go back to the code, I would put A here, RA0. That's all I would have to do. If I want a B pin, RB3, it's tris B bits RB3. And the same with the port commands that we saw. Right? So the letter refers to the port, A, B, or C on our chip. Right? And then which of those pins that you want to use. Okay, so we have the two-color or bicolor LED flashing on and off. We would like to be able to control how fast it switches back and forth. A couple of things you need to know. Our PIC MCU has a certain operating or processing speed. It runs, the default speed is 1 megahertz. We could make it run up to 32 megahertz. We could make it run at, say, 125 kilohertz. So we can make it faster or slower. The time unit used to talk about times on a PIC is the instruction cycle, TCY, T for time, instruction cycle. Okay? It's the minimum time for any operation, like to turn one of these pins on. One instruction cycle is 4 divided by whatever the operating speed is. Okay? It's 1 megahertz here, so 1 million. 4 divided by a million is 4 microseconds. Get used to this prefix. That's mu. The Greek letter mu stands for micro. 10 to the minus 6, in other words. In my code, I used some delay operations that are part of the xe.h. One of them is NOP, which just means one instruction cycle. But the one we're interested in is underscore delay and then a number. It's got to be a long number. Longs are much bigger than integers. They can go up to about 4 billion, right? But for us, cycles cannot exceed this number. If you put in 200,000, you'll get an error message when it tries to compile. Right? So this is a number you need to remember, 179200. That's the maximum number that can be inside a function call here. There's another function called underscore delay 3, where it takes a unit a number of type character. Character only goes from 0 to 255, so the maximum here isn't too big. It'd be 3 times whatever unit is, and times TCY. Let's look at a simple calculations here. Okay, so in the code, I had underscore delay 100,000 UL. The UL means unsigned long. This is just a little precaution because the C compilers tend to think of bare numbers like this as integers, and this is too big to be an integer. So this is just a warning. Make sure this is actually put in enough memory space for a long number. Okay? So 100,000 times 4 microseconds turns out to be 0.4 seconds. Right? If this was 10,000, it would be 0.04 seconds. Delay 3 times 100, we didn't use this guy. It's 3 times 100 times 4 microseconds. That would be 1.2 milliseconds. Milli is 10 to the minus 3. Okay. I should mention that there are some other timing functions that are, in some ways, are a little more useful. There's something called underscore underscore. This looks like 1 underscore, but it's actually 2. Underscore underscore delay underscore US. That looks like microsecond, right? This actually is going to give you delays in microseconds. Float means X can be a decimal number. And here's another one, underscore underscore delays underscore microsecond. Pretty sure that was a typo. It's delay milliseconds float X. Something you have to be careful about. If you want to use these two functions, this statement has to go up at the top of your program after your include files. It's called a define statement, and it defines something called crystal frequency, and you must tell it what you're operating at. We're typically operating at 100,000, but not 100,000, 1 million, 1 megahertz, but it could be 32 million or 125,000. There's an entire range of frequencies we could use. It needs to know this number to do this correctly. Also, what's a little something that you have to be careful about is that you must make sure when you choose X that the X does not give you a time less than 1 instruction cycle. Your program can't do that. Or it can't give you a time that's greater than this magic number 179,200 TCY. You're going to need to be able to calculate times appropriately in terms of instruction cycles and maximums and minimums of these guys that will work for you. That's all. That's all the code you need to make your programs turn a pin on or off so that you can light up an LED. So, just to cover it again, include this library in your configuration bits. triscbits.rc3 equals 0. That turns that into an output. Means we can set it high or low. portcbits means do you want it to be high or low? So this makes it a digital output. This sets the value of the digital output. You need to know a little about how LEDs work to make them light and how you make connections with them. And if you want to do anything cool, you usually need some sort of delay function in here to make lights blink. And as mentioned in the code, if you cut this down to something like 100 instead of 100,000, that flashing will be so fast you won't see red, green. You'll see a continuous mixture of them that will look kind of yellowish or orange depending on how long a time you've chosen for. That's it. Thanks for now.